The floor is yours.
Thank you very much. You excuse me, I might sit a little bit because my legs are not holding too well. Anyway, so we have about 30 minutes, roughly speaking, correct? What? Yeah, 30 minutes. The title of my talk is Scientific Methods in the Era of Big Data and Machine Learning. As you know, folks, currently there is really a fashion, if to put it very mildly, on this machine learning, deep learning, and all these big words. And so I prepared a little talk on, well, I hope I can, okay, good. I prepared a little talk of warning you. And this talk is really aimed mostly to the students and rather than to the faculty. But I just want to challenge you that just to hack is not good enough in academic research, okay? And this deep learning gives this misimpression that that's the only thing. You just take a lot of data and you put it through the black box, and long behold, good things will happen. Well, that is not good enough, at least not for me, and it shouldn't be for you, okay? So let me just go on. So science in the era of big data. So let me just go quickly. Definition, you know, we probably don't need to, let's see. Let me just go through this. Oh, sorry. Okay. Well, I'm having some hard time with this display. Okay. Okay, never mind. All right. Okay. Okay, I'm here. So,
it's not working.
Huh?
The image.
It's not working?
It's working now.
Okay, good, good, good. I may need to just put it down, this microphone, this way, and just go on. All right, so what are the scientific methods? I hope that Laura's presentation showed you the foundational approach that I am teaching the students and in my group that we take. Yeah, I think that might be a better, because this way I might have a little bit more. Okay, here we go. Okay, yeah, this is fine. Thank you. And so basically what she showed you is she identified the problem. How do we get local muscle forces? And this is so critical, folks, in any human-robot interaction if you really want to have a predictive dynamical model. We have motion models from Newton with all the inertia and velocity and acceleration and forces, but you need to get somehow these parameters. With robots, you can measure the hell out of them and you can get the complete model. But for the human, it's really a question what you can really put into. And so in order to do this collaboration between human and robot, you really need two equations on both sides, one from the human and one for the robot. And for that, you need the muscle forces. So she identified the problem. Then she painfully got the data, and she showed you quite eloquently that how difficult it is to get good data. And then, based on the data, makes you hypothesis formatted from the data observation, and then you do validation, empirically tested. So the classical model of scientific inquiry from Aristotle, it's not new idea, who distinguish approximate and exact reasoning. And you are in AI, so you know probably about the abductive, deductive, and inductive inference, right? I mean, specifically, more about deductive and inductive inference has been a mantra of artificial intelligence. But there also has been reasoning by analogy, okay? Now, recently, statistics came much more into prevalence because the data is noisy. Measurements are noisy, so you have to think about Bayesian inference. Okay, now let's see next. So there are formal theories. I will not dwell on this. You probably, those of you who are in computer science must know about axiomatic theories, how you derive the assumptions that those are your axioms, but you probably know about arithmetic is an axiomatic theory, multiplication, you have to have identity system and so forth. This is well known. I'm just having it on the slide so that it reminds you that you should not ignore it. Okay. So theories and theorems. Okay, so theory is an explanation of some observations. Theory is the reasoning behind the law. And you know, if your deep learning proposes a new inference or a new law, you better check it how it encompasses the old law. How do you compare, let's say, classification with the neural network and your feature extraction? And if they don't agree, then you better tell me why. Okay? What's missing? And not just say, you know, the students come, look, Ma, it works. Okay. Tell me why it works. And where my standard question in PhD exams is when it fails. Don't tell me how it works, but tell me where it fails, because then I know you understand your system. All right. Now let's see. What did I do now? Okay, all right. Okay. Don't worry, it's my clumsy hands. Yeah, that's it. All right, so.
I'm sorry, it's not working.
It's not working?
No.
Uh-oh.
But.
You know, I tell you, you don't know this, but in this school, there was a Professor Kneppo. Does anybody recognize the name? Yes, sure. Okay. He taught electrical engineering, and I took his course. And he always said, if there is a problem, it's connection. And in electrical engineering, that's absolutely correct. Okay. So science in the era of big data. Am I on? Are you okay? All right. So observations, as Laura pointed out, I am obsessed with the good observation, depend on the apparatus that performs the observation exercise. Hence, during the history of science, the sophistication of explanatory power of the theory, laws, and more models depend on the capability of the observing sensors, including range, spatial information. And initially, we were restricted to our human eyes, ears, tactile sensor. Later, of course, technology proceeded, magnifying glasses, optics. You see, I have my glasses, facilitate discoveries of celestial movement, probing sources such as microwaves outside of the visual spectrum, penetrating materials, and high energy accelerators enable discovery. Now, so, it has been accepted in the scientific community that observation is more informal, while measurements performed via scientific instruments are more quantitative. Now, this is, folks, very important because notice I have this. Data is not reality. And I know many of you are computer scientists and you think data is everything. No. Because you really have to understand where the data comes from and how it was transformed into your bits. Got it? I hope so. Good. All right, I get very emotional about this. There exist some standard methods to control quality of data. Select the sensors, and you saw that on Laura's explanation, with some spatial temporal signal to noise capabilities adequate to the problem at hand. Then perform calibration, because every sensor has limits, and your data will have those limits, okay? Then select the proper sampling in order to achieve desired performance. And then perform controlled experiments. And this is especially important when you work like we do in our lab in healthcare. I mean, imagine if you magically say, oh, you have a cancer, but it turns out you don't. Or they diagnose that you have something else, and they start to cut you. And they find out nothing, all right? That's the fallacy of this whole thing, and the danger. Okay, so I think, discoveries and explanations. So I just want to tell you, I am not against learning. It would be stupid of me if I would do that. But I advocate careful experimental data collection. This doesn't imply negation of explanation. Now, there are good examples, and some colleagues pointed out to me, that, for example, James Watt, and this is relevant to Žilina, was playing with steam engines, okay? Steam generators, basically. He didn't know anything about thermodynamics, all right? But he invented steam engines. Later on came people like Bernoulli and others who really looked at the performance of his steam engine and put it into thermodynamical theory and equations. So similarly, you know, there are some other examples, and I will show you some examples. So, but machine learning is an empirical phase at this point. It's not really a theoretical science yet. There is still a lot of mystery in why and how neural networks work, which causes some discomfort to Ružina Bajci. However, deep learning opens many new problems and ideas as opposed to refinements of classical results. And the interesting thing what this deep learning is doing is that, you know, it allows you to look at a much bigger complexity of problems and much bigger size of problems, which do not allow you to apply the classical models. The good example I will tell you, you probably have, you may not have heard about Hamiltonian equations, okay? Well, at this moment, we have the Hamiltonian equations can deal with 6 to 9 dimensions. If you want to apply them on a human body, there are many more degrees freedom than even 12, right? I mean, just think about it. You know, your wrist has 2 degrees, your elbow has 3 degrees, and your shoulder has another 4 degrees. So there you go. And for each degree of freedom, you have three dimensions. So calculate the number of dimensionality. So, you know, these methods allow you to ask at least questions how to deal with this large dimensionality. Now, you still somehow owe it to yourself and the scientific world explaining what works and what, and we should strive for reproducibility and repeatability. All right. Okay, so you know, yesterday I was giving similar lecture in Žilina, and it turns out that in the morning before the lecture, I got this email from a former student of mine of from this email from about this paper that Professor Zitko from Harvard Law School wrote about intellectual depth. With great power comes great ignorance. This kind of discovery, popular because of big data and ML, answers first explanations. You do first explanations, and later, I call intellectual depth. We gain insight into that works, like the steam engine, without knowing why it works. We can put that insights to use immediately and then tell ourselves we will figure out the later. And I'm sure you have heard that before. Sometimes we pay off the debt quickly. Sometimes, as with aspirin, it takes centuries. It was discovered 1897, aspirin, but explained in 1995. So you see the big difference, all right? Now, there are some consequences, and I will not go through them because I promise that it will be only 30 minutes. But there are some consequences. For example, this Royal Bank of Scotland applied the routine patch to software it used to process transactions, and it went poorly. So, you know, you have to be careful what is the domain where you are applying this machine learning stuff, okay? Okay, banks are particularly susceptible to technical debt because they computerized early and invested heavily in mainframe systems that were and are costly and risky to replace. Imagine that you would be still having code from Ural 2, all right? And how would that kind of translate, all right? Okay. So, unpaid intellectual, why is unpaid intellectual debt worrisome? There are at least 3 reasons in increasing the difficulties. And in particular, so I will send it to you so that those of you who are interested, you can read it later on. But the important thing is that depending on your application, if you are doing what my colleague Jitendra Malik does, segmentation, all right? And he takes a bunch of images from Google and has a bunch of undergraduates outlining some of them, and that he uses for training segment. If he makes a mistake, who cares? But, folks, if Boeing 337 crashes, and you tell me, oh, the program worked 99% with accuracy, how would you like to fly a plane where you know that every hundredth of the plane will crash because that's the 99% accuracy is telling you, okay? So depending on whether they are life critical or not, apply, you know, these techniques. You can publish, but it doesn't matter. All right. And most profound issue with intellectual debt is the prospect that it represents a large movement from basic science towards applied technology. I mean, you know, and I've seen this. The industry goes gaga about this. It's incredible. They are throwing money at our students and some of my colleagues. And I saw this before. There was AI in the late 80s, rule-based system, same thing. And then, guess what? The rule-based system shown it works somewhere, but it has limits, all right? So then it was the winter of AI. Now we have the spring or summer of AI. But, you know, we have to be responsible. Okay, enough. All right, so let me just, no. Okay, what should we do? All right, so yeah, when the stakes are low, such as the use of machine learning to produce new pizza recipe, it may make sense to shut up and enjoy the pizza and never fret about the theory behind what makes peanut butter and banana work so well together. But when the stakes are higher, such as you use AI to make health predictions and recommendations, we walk on untested ice when we crib, the answers and test rather than ever learning the underlying material. So, all right, so now enough of this warning kind of situation, and I am not the only one, you can see that, but you know, our credibility is on the line, so we really have to be very careful how we use this new technology. And there are some serious problems like optimization, how do you choose the proper space in which you are examining these deep networks. So I'm not saying everything is bad, it's just you have to be careful. All right, so let me just show you what my students are doing, just as a sample. So here is Caroline Chen is working on haptic perception of liquids enclosed in container. And the reason I like this, I mean, by the way, each of my students has a different problem. And partly I do that because I feel they shouldn't compete with each other. Secondly, you know, if they pick their problem, you know they will do the best, as opposed to Ružena Bajci telling them. The only thing, my function with these students is, I look at it, I read it, and I say, hey, maybe you should not try this because I tried it and didn't work, so go this way maybe, and you know, that kind of advice. But I never tell students what they should be working on. So this problem, Caroline came and she said, well, Ružena, I would really like to examine, you know, if you have a container and you have a robot and then you have some kind of material inside, what is the dynamics of how to control so that I don't spill, that things moves properly in a controlled manner. And initially I thought, well, you know, this is interesting, but then I started to look at the physicists are interested in this. And I tell you why, because water is okay. I mean, you can do fluid dynamics, applied fluid dynamics equations, and you will get the right answer. However, it turns out that sugar, flour, you know, like cereals, those materials are not obeying, they are not firm, they are not continuous mechanics, but they are not behaving as fluids either. So the standard machinery that is out there from physics doesn't apply, all right? So the physicists are now looking at, because these little pebbles or particles, as you are moving them, they clump together and they change different shape. And when there is a different shape, the wall surface traction gets involved and gets important. But if you really want to build a robot for home, or for that matter, even in a civil engineering, when you have these big craners and you are pouring concrete, for example, same problem, okay, same problem, okay. So I feel this is a very nice problem, and she's making some progress. Okay, so here is using the estimation of liquid volume, determine the angle of which to pour a precise volume of liquid, and here are the equations. And so, okay, so you can probably go on her website and read full papers. Now, the second student, I mean, Laura is first, you know, Caroline second, Isabel third. She is interested in developing new tactile sensor finger. So she's using, and this really falls into, have you heard about soft robotics? I hope so. So anyway, this is along the area of soft robotics, and she developed what she calls Ceph cell, and it's basically using well, here you see and she designed this and built it basically. That's why I was hammering on you, Joseph. Get the students, open the room, and let them build whatever they like to build. It's important that they can play. Anyway, so she put on at the end a camera, and then on top of it, kind of elastic materials with holes, so that as you press, you can read out much better than the typical pressure sensors. So it's a more sensitive tactile sensor. And we are hoping to use it, for example, for applications. You know, the airplanes, when they land and they are being inspected, there is a need to do very quick inspection whether you have some brakes on the plane. And so we are hoping to put this sensor on a mobile platform and examine quickly whether there are any cracks on the plane, because then these sensors can depict it, okay? So, all right. And we'll see what other applications will come out. So here is read geometry and force, so it can read equally geometry and forces. Now, this is Robert Matthew and modeling, and you saw Laura was showing you that we really studied this muscle stuff, but there is a rationale behind that, and that is, this just has a conclusion, sorry. Let me go back. The reason for the muscle, we studied this interaction. You can see the human-robot interaction. And in order to really have a predictive model that can predict how much you have to help this human, think about it in an old age home. You have to, these nurses have to lift old people to put them into the bathroom, okay? So my idea was that what if this human would be a nurse and the robot would help, but it has to be very flexible because humans are not rigid bodies, okay? So the rigid mechanics, no. So this is the soft mechanics has to be implemented, and so they can help them, because many of these nurses get very bad backache because they have to lift these people. So it's a very humanitarian application, but we are not yet there. I mean, we are waiting for Laura and others to finish, you know, make improvements. All right, so summary and conclusion. It is widely acknowledged that science we stand on three-legged stool, theory, experiments, and now, of course, computation. When I was here, computation didn't exist, okay? I mean, it was starting, but didn't exist. Unfortunately, it turns out that many theoretical models, equations, are not amenable to fast or large-scale computation, okay? Hence, it behooves us to re-examine these models, reformulate them to admit computation, and bring the technology to new applications. All right, and here are my beloved students. As you can see, most of them women. Robert is leaving, so there will be only women, and I'm very proud of it. Thank you. All right, what can I do? All right.
So, the very first question, how do you manage to have so many girls, women?
By accident, I guess. I honestly, you know, as you know, the whole world is trying to equalize, you know, the fact. Look, when I started electrical engineering, folks, there were 300 students in the first year. And there were here in Bratislava, on Vazova, remember? That's where the university was. And there were 15 women. By the time we finished, there were about 120 men and 3 women. That's it. So anyway, everybody is recognizing that we really need to equalize the women participation in technology, okay? But so Berkeley, the same thing, you know, everybody's trying to hire more women and I didn't very much, you know, they just kind of came. I guess my accent, maybe. I don't know. Anyway, I love them all. They are my extended family because my children are all over. So they are my extended family, and I treat them accordingly, as probably Laura will tell you.
Okay. I'm still thinking about what you have told to give every student his different topic, because I believe that every student should have as much freedom as possible.
Yes, yes.
But actually, to be honest, my strategy was all the time a bit different. To make students to work together, but I'm not very successful in it. So finally, they have their own problem as well. But initially, I try to connect them. And my question is how they are connected, or whether they are connected. And
I think Laura should answer that question.
Yeah, I mean, even if we're all working on our own problems, I think there's certainly a lot of interaction. Like, I mean, we all just went to a conference together and it was lovely. I think, so, you know, we're all, or mostly all, I think people are working more on, you know, the soft robotics and the just automation stuff now, but, you know, there's also a lot of us working on human modeling from different, you know, I'm a little bit more basic science right now, but Rob and Sarah are a little more applied, and that's a really important perspective. And a lot of, you know, a lot of the math translates, a lot of the different techniques translate. So, you know, within our group, but also I think one thing that, if it's not true here, maybe to work on is, I don't just talk to these people. I talk to people in all sorts of other, like within the EE department controls. There's several other groups. I sit in a giant cube farm with a bunch of different students in different labs. Talk to them all the time, hear their perspectives, get very distracted and don't do any work sometimes. But you know, even, you know, across departments, I know people in integrative biology. I know people in mechanical engineering, and in particular, the kind of work that I do is extremely interdisciplinary, and so it's really important for me to be talking to people in a bunch of different areas. So I think it's totally possible to all have independent projects and still, you know, share a lot of the math, share a lot of the help. And you'll notice, you know, when, you know, she presented Isabella's project and Carolyn's project, but there were other students listed as well who had kind of contributed and helped out, who are, you know, also in the lab. So.
Can I add to it?
I do believe, because you are successful.
Yeah,
so
yeah. Berkeley. One of the advantages of Berkeley, and you can do the same thing here, has that every professor has some kind of orientation, okay? And for example, I collaborate quite closely with Professor Tomlin and Shankar Shastri, and their students and my students are interacting quite a bit. But the most important thing is that there are so many seminars. Almost every day we have a seminar. And so the students kind of pick and choose, you know, what they hear and what they go. And then there is also a kind of underground, this kind of mingling between different students. For example, the machine learning people who are not exactly with Tomlin and Shastri, but there is Michael Jordan and a few others. And those students occasionally kind of rub shoulders. So there is a lot of interchange. Do you see what I'm saying? And furthermore, we have also a lot of interchange among different departments. And I would like to emphasize that because you folks still adhere to this old-fashioned, you know, electrical engineering, computer, mechanical, blah, blah, blah. You know, we have, in my course, for example, robotics course, I have students from bioengineering, from mechanical engineering. I don't know whether I had from other, oh yeah, mathematics also came. And there is, you know, people invite each other to seminars, so there is a much more fluidity between different departments. We write proposals together, you know, and that's another strength that, you know, in fact, many of these agencies, when they are looking for bigger grants, they want you to have a cognitive scientist and a mathematician or statistician or, you know, whatever else.
We have a question there.
Yeah. Dear Professor Bajcsy, here I am.
Yes.
You might know there is some Hungarian mathematician.
Yes,
he had
speak up a little bit. I can't hear you too well.
Why?
Okay.
Okay.
All right. So, you come from mathematics. I heard that. All right.
You should better articulate, maybe. That will be enough. No. Not batteries. Another problem of our age. Batteries.
Okay, once again. Okay. There was a Hungarian mathematician having a quite interesting theory on the history of mathematics.
Okay.
And he said basically that each great mathematician had one idea, except Newton, who had three. In this respect, I would like to ask you if this applies to your scientific legacy and if there is one profound idea which you keep elaborating throughout your career. Can you explain? Can you share? Thank you.
Okay, so let me just say, I hear around here that there is a really pressure on many of you, publish, and this age factor or whatever factors you measure, it's kind of, so let me just say that if you are lucky, you have one good idea in your lifetime. I was very lucky, I had 2 good ideas, that's it, no more. And my first good idea was this active perception, where reading all kinds of articles, and so I came to conclusion that at that time, the people in computer vision, they were just taking pictures, and it was much more static. And the active perception sort of implemented or formulated the idea that vision is active, that we are not only seeing, but also looking. Now, let me just say that the first time I submit a paper on this idea was turned down. And this is not, you should not be surprised. If you have a new idea, there is a lot of conservatism in the community. There is, in America, we have this NIH, not invented here. The reviewers feel, well, if I didn't think of it, why can it be any good? And you have to have a broad enough reviewers in order to accept your. So it took me 3 years to publish the first paper on active perception. Now, the second idea I had was this digital in anatomy atlas. And that was motivated when I was at University of Pennsylvania. A rather well-known biophysicist, Britton Chance, I don't know, maybe you have heard of him, those of you who are in biophysics. He was a quite well-known gentleman. And I was a young assistant professor there, and he sort of sent me an email, Ruzhna, I have some images, maybe you have some techniques to process them. So I went to his group meeting where they discussed problems. And yes, indeed, he had some images which were not very interesting. However, I was listening to the doctors at that time, how they analyzed the CT images. You know what CT images are? These are computerized tomography X-rays, okay? Now remember, we are talking about 1973, 74. And it was fascinating because these images were digital images. They were come out from reconstruction from the computer. But the doctors didn't know how to interpret them. So what they did was they took these slices and they printed them on a film, and they looked through the windows to really recognize what it was there, because they couldn't interpret what the screen was telling them. It took at least 2 generations of medical doctors to train them to learn how to read the computer screen. But I also noticed that with these images, they would get a series of 3 slices of 3-dimensional brain, for example, but they again couldn't recognize the 3-dimensional brain, so they had to look at just slides by slides. And it was a lot of speculation, and so then but they used the anatomy knowledge, okay, to delineate some of the anatomic structures. And that idea gave me that, hey, well, maybe I can design an algorithm to do that. So what I did based on that, I took there are these paraffin brains that people have, and you can slice them very thinly. Human brain, but of dead people, of course. And so I took and I digitized those slices, and I reconstructed the 3-dimensional brain, which I call the atlas, because there are certain structures that are invariant from person to person. Now, the positions and some of the features are different from person to person, but basically you have 2 halves and you have certain structures on the brain are the same. So I took that and made it as a knowledge, and then implemented what I called an elastic matcher from the data on this atlas. And the reason was elastic was like a rubber sheet. I took the CT scan, put it on the rubber, and then, no, I took the atlas, put it on the rubber, and then adjust it to the data. And that was first time, and everybody, well, that paper got accepted rather immediately, because I had some collaborators, doctors on the paper. So that gave a credibility. I'm sure if I would be alone, it would be waiting for 3 years. So, and since then, I did a lot of other things, but none of them were so foundational. I'm hoping that, you know, the muscle will be of that kind, but we'll see how that works out. So, yes. Did I answer your question?
Thank you very much.
Yeah, go ahead.
Thanks for a very interesting presentation, in which you mentioned that data is not real. Do we have to get only more measurements or more accurate measurements, or is it better to include those inaccuracies in the data models used for modeling of real physical?
So let me just tell you, it depends on what your goal is, what your task is, okay? As I mentioned, I forget the name. He's a professor in Washington University. He used, by hand, he picked different pictures on the Google from Rome, from the Colosseum. Okay, and then he used geometric reconstruction, which is, you know, matching and reconstructing, and he reconstructed the three-dimensional Colosseum. All right. So in this application, let me just say that if there is a centimeter error, who cares? You look at it, say, oh, this is beautiful. It's Colosseum in Rome. That's it. That's your goal, and that's you accomplished. On the other hand, the work I did well, maybe about 3 or 4 years ago, we worked with muscular dystrophy doctors. And these doctors, I mean, the muscular dystrophy as a disease, I don't know if you really know what it is all about, but it's basically a disease where the muscle fibers are getting weaker and weaker. And it's a genetic disease that you are born with. And then eventually the muscle is not elastic at all, and therefore crushes your skull, I mean your bones, and you die. So typically children who have this around age 15 or so, they die. And I think they are now trying to find as far as I know, there is no really cure at this point. So I collaborated with a doctor who treats these patients. And the idea was that he wanted to have a diagnostic device of how much these children can do this. For example, can brush their hair or do this, you know. So, so that's a very nice problem of kinematics, because you don't have to do dynamics very much. So but the condition of the doctor was that it has to be cheap. That's one of the constraints that the doctors give you. So we decided to use for recognizing the joints, whether you can do this or whatever, using Kinect. You know the Kinect camera? Are you familiar with Kinect camera? Okay. There are 2 Kinects, Kinect 1, Kinect 2, and they reconstruct the 3D in a different principles. One is doing it with a LiDAR, kind of. They shoot some microwave and measure how fast it comes back. And the other one, I think, is on some kind of a stereo principle. I'm not sure, I forgot. It's a long time ago. Any case, the bottom line is that we have calibrated these 2 cameras. And let me tell you, one of the cameras to detect your feet gave us 5 centimeter error okay? The other camera was only 1 centimeter error. So for these medical applications, I think error assessment of the measurement, all right, and is important, because then it's a diagnostic tool and tell you how well you are doing. So with this measurement, what we did was we created, the workspace. Do you know the concept of workspace? It's basically XYZ space of reachability, how far you can reach. And so we could show that how this tool, by measuring the volume of this reachability, okay, was shrinking and shrinking over time. It's now used on, I don't know, thousands of patients in UC Irvine in the medical school.
Okay, so we have the last very short question.
Yeah, go ahead, please.
Madam Professor, my question is about cooperation. I read the interview with you in Forbes when you recollect your entry to Slovakia after 1989, and regretfully you said that Slovakia was not ready for cooperation in that time, and you went to Prague, and there was the Center of Machine Perception created, very successful center with your help. So after, maybe we lost 30 years, but do you see the possibilities for new chapter, turning the list and starting the new cooperation now?
I agree, of course. Yes, I do.
Okay, so this is...
What else can I tell you? I mean, look, guys, make a proposal. I mean, that's what, I used to be at the National Science Foundation, so I'm familiar with proposals. Yeah.
Okay, I couldn't imagine the best conclusion of this nice event, as I really believe that one day some maybe people from this room will come to Berkeley, or some your colleagues will come here. I really want once again thank all of you who probably interrupted some vacation or some other important stuff in recovering during summer.